That kind of covers all our housekeeping stuff. So let's get started right away. And let's welcome our co-host from Bogota, Colombia, Gonzalo Gallo, local moderator for the ACI Colombia chapter.
Well, good afternoon and morning and night to everyone. Thanks, Scott, for the introduction, and Bernie for putting this together, and ACI, of course. Here at the Colombian chapter, we're happy to participate for the sixth year in a row in this great event. We're a long-standing chapter since 1977, I think, one of the oldest chapters outside the US. And today we'll kick off the presentations with Daniela Martinez. She's an assistant professor at Universidad del Norte in Colombia here. She earned her master's and PhD from the University of Berkeley, and she works on the chapter, So with no further ado, we'll hear Daniela's presentation.
Good morning/afternoon, everyone. My name is Daniela Martinez, and I'm an assistant professor at Universidad del Norte in Barranquilla, Colombia. Today, I will discuss Roman concrete, and one of the questions that has fascinated researchers for decades. Many Roman structures have survived for nearly 2,000 years without Portland cement. And because of this remarkable durability, Roman concrete is often presented as a model for sustainable construction. But is Roman concrete actually more sustainable than modern concrete? And if so, why? Today, I will share the results of a study that we conducted that aimed to compare Roman concrete to modern concrete using life cycle assessment methods and be able to identify lessons that may be still relevant for today in the context of decarbonizing our built environment. So why should we care? Concrete, as most of you know, is the most widely used construction material in the world. Every year we are producing roughly 30 billion tons of concrete. And because of this enormous scale, concrete has a significant environmental footprint. In fact, cement, which is the main ingredient in modern concrete, along its supply chain is responsible for roughly 8% of global CO2 emissions and approximately 3% of global energy demand. So this challenge motivates the search for alternative materials, alternative production methods, and lessons from historical construction practices that we can apply, hopefully, in our modern infrastructure. So let's talk a little bit more about the Roman concrete infrastructure. Roman concrete has attracted attention because many Roman structures remain standing today. These structures, like I mentioned before, have survived more than 2,000 years and were built without Portland cement. Some of the most famous ones I'm showing here in these pictures are the Roman Colosseum, the Roman Pantheon, markets of Trajan, etc. So we have asked, did the Romans discover a more sustainable way to build, and are there lessons that we can apply today? So the common assumption usually is that if we have Roman concrete that has lasted longer, therefore Roman concrete must have been more sustainable. So our study specifically asked two questions. Is this actually true? And could Roman technology help us decarbonize construction? But first, we need to learn or revisit what was Roman concrete. Roman concrete consisted primarily of limestone, which is one of the main ingredients, the raw materials that we use today in our modern Portland cement. And this limestone was also heated to a certain level to obtain quicklime or hydrated lime, like we normally do with our modern cement. But this product was also mixed with volcanic ash, which is a pozzolant, and mixed with water to form a mortar. And this water was often seawater. And this Roman mortar was then further mixed with big chunks of fragments of rocks or rubble from debris from other demolition sites or construction. And this massive concrete was what was used in Roman infrastructure. So like I mentioned before, limestone first was heat treated to obtain calcium oxide or quicklime or hydrated lime, depending on the mechanism. But limestone had to be first calcined in some ancient Roman kilns that were typically fired with using biomass fuels. These biomass fuels were usually just wood that they had in the surrounding areas. And in order to obtain quick lime, the kilns were fueled to lower temperatures, usually 900 degrees Celsius, more or less. So the key chemistry in Roman concrete was activated by the pozzolanic reaction. Now, this pozzolanic reaction means that the volcanic ash would react with lime to form additional cementitious compounds such as CSH over time. So this is the first difference with our modern concretes, where CSH is also the binding mechanism, but it forms rather quickly and not over time like with Roman concrete. In contrast, modern concrete consists of Portland cement mainly, and water that constitutes the mortar, and then we mix it with aggregates. In contrast with Roman mortars, the Portland cement needs to be first obtained with a mix of clinker and gypsum, and clinker is produced with much higher temperatures in our rotary kilns. These higher temperatures roughly reach 1,450 degrees Celsius. And unlike Romans, we have heavily relied on fossil fuels to be able to power these kilns to the temperatures that we need to reach in order to produce clinker. So like I mentioned before, modern concrete, the way it works is that cement hydration, when we mix Portland cement with water, cement hydrates and starts precipitation of binding products that are also the type of calcium silicate hydrates, or CSH, and these are considered the main binding phase. But this formation of these binding phases happen rather quickly and not over time or slowly. Now, since Roman concrete was not made uniformly, we needed to establish certain parameters in order to determine what mixes we were going to use to compare to those mixes that we typically use in modern concrete. So we basically started with our reaction of our raw materials that form the Roman mortar, and then we add aggregates and we obtain Roman concrete. The Roman mortar formulations we draw from different reports and studies in literature, and we determined that we were going to model 3 types of Roman mortars, usually found in literature from Roman concrete reconstruction. So the ratios were 1:2, 1:3, and 1:4, and these vary depending on the ratios of lime to pozzolan. These formulations form the basis of our environmental comparison. So then, how much energy did Roman concrete require? Many people assume that lower temperature production then automatically means lower energy demand. Surprisingly, that was not always the case, as we can see in this bar diagram, where we're comparing energy demand on the vertical axis and the different formulations that we study on the Roman concrete and mortar formulations across different production scenarios compared to the modern counterparts. The modern counterparts we can see here, modern mortars are these gray bars, and modern concretes are these other gray bars. The rest of the bars correspond to Roman concrete formulations, the 1:2 ratios, 1:3 ratios, 1:4 ratios, and it will vary depending on the production scenarios and the technology used for production. So we study all the way from their Asian method to make these materials to the average modern technology that we use nowadays, to a production depending only on biomass as fuel in the kilns, and all the way to fully electric calcination for limestone using decarbonized electricity. So surprisingly, Roman concretes were not always less energy intensive, even though they use lower temperature materials, and often require more energy than expected, particularly when inefficient kilns were analyzing the Asian production technologies, like we see here. And with Roman concrete lower carbon If we also see this bar diagram that's comparing greenhouse gas emissions on the vertical axis, but this one is looking at each formulation of concrete by cubic meter, so by volume, we can see that the answer was generally no. It was not lower carbon. Under modern production conditions, Roman formulations typically increase greenhouse gas emissions compared with conventional concrete, like we can see again here. These bars correspond to modern formulations, and the color bars correspond to the different Roman concrete and mortar formulations with the different production scenarios. Therefore, the surprising result is that Roman concrete was not necessarily automatically lower carbon or had lower CO2 emissions. We could see that there were some lower results compared to modern counterparts when we start looking into formulations that use more pozzolan, like this one that was 1:4 ratio of lime to pozzolan, and also the production scenario meant that the calcination was completely done by an electric calciner using the carbonized electricity. The Roman formulations generally increase emissions when produced using modern technology, except for that final case. Now, while Roman concrete did not consistently reduce greenhouse gas emissions, it did show significant reductions in other air pollutants, which are precursors to compounds that can be harmful to human health. So when we look at estimates on nitrogen oxide and sulfur oxide emissions, or NOx and SOx, we see a big reduction compared to modern concrete production, all the way from 11% to 98%, depending on the production scenario that we were analyzing. So these benefits were observed, good benefits were observed across fossil fuel, biomass, electrified production pathways. Of course, with the largest reduction when we model electrified calcination of limestone using decarbonized electricity. So since NOx and SOx contribute to air pollution and adverse health impacts, then these Roman-inspired formulations may offer benefits beyond this carbon reduction or embodied carbon. Now, like I mentioned, while Roman concrete offers some reductions in CO2 and significant reduction in other harmful air pollutants, the most important observation that we can draw from our analysis is that the biggest insight is not the Roman mixture itself, but the way they use to produce it. And so in this case, the real reason why it was more sustainable was because the Romans rely almost entirely in biomass as fuel for their ancient kilns. So this was interesting because we look at if we had used biomass in our modern construction using modern concrete, but relying solely on biomass to produce clinker, then the potential savings of producing all these modern concrete or modern cement relying solely on biomass would have been 3.7 billion tons of CO2 equivalent. CO2 equivalent is the unit that we use to measure the impact of CO2 emissions and other emissions that contribute to greenhouse gas effects. And this was a big number. It corresponds to roughly 11% of annual global anthropogenic emissions, which is interesting to understand. As we rely on this biomass as fuel instead of fossil fuels, which we typically use, an example of it is coal, then these could have been the savings that we would have had all these years. Now, another aspect that we looked into it is how longevity, because these structures have been standing for so long, how longevity plays a role in the sustainability of the mix itself. And the idea is that we ask ourselves, can longer service life offset higher production impacts? If we are seeing that modeling these Roman concrete and Roman mortar formulations with our modern technologies still sometimes produces higher embodied carbon than those modern mixes that we use nowadays. So if we have a longer service life, like we've seen in the Roman structures that are still standing, then that means that we're going to have a structure that needs fewer replacements, and therefore there's going to be a lower material demand, and these would eventually lead to lower cumulative emissions. So with this premise, we also look at another aspect of modeling infrastructure using Roman concrete formulations. Because if this is actually true, durability is also important in reducing upfront embodied carbon emissions of our materials and our infrastructure. So we did a preliminary assessment on how much longer would Roman concrete need to last in order to break even or to offset these embodied carbon emissions that are much higher than modern concrete in some of the production scenarios that we model. So to answer this, we compare Roman and conventional concrete under several production scenarios, like I mentioned, and different applications as well. So in the case of buildings and residential and commercial infrastructure, where with modern concrete, the typical service life is about 70 to 90 years. And this is data from the US. If we model this infrastructure by using Roman concrete in order to offset higher emissions upfront from Roman concrete formulations, these structures would have needed to last 41% to over 3 times longer than the time that is reported with modern concrete mixes in buildings and residential and commercial infrastructure to be able to start making sense. So modern production of Roman concrete would have required a lifespan of 41% to over 3 times longer to offset these higher production impacts. Now, if we look at, which is more interesting to look at shorter-lived infrastructures such as street and highways, which their typical service life is smaller, 45 years approximately in the US, then the numbers start to be reduced and make more sense. If this infrastructure or this application would have been made with Roman concrete, then it would have lasted, or it would needed to last 29% to 97% longer to be able to offset these higher upfront impacts. The shorter-lived infrastructure offers the greatest opportunity for emission reductions through increased durability. Now, our key conclusions from this study are that Roman concrete was not necessarily more sustainable to produce upfront, specifically when we're comparing by volume, by cubic meter of material, but it offers important lessons regarding fuel selection, durability, and long-term environmental performance. So Roman concrete, by mixture, if we compare it to modern concrete, is not automatically greener, but biomass fuel use offers valuable lessons, specifically when looking at alternative fuels to power kilns, which is one of the big contributors to CO2 emissions in the supply chain and the production of cement and therefore modern concrete. And longevity of these structures may be an important sustainability benefit over the life cycle of infrastructure. So how can we adopt longer service life for infrastructure in order to also become more sustainable, because we need less material, less repair, less maintenance, and therefore less emissions as well. So this concludes my presentation, and this is my contact info on the bottom of the slide. I would like to thank you all for your time listening to these presentations, especially to ACI for hosting this incredible event. And now I welcome any questions that you may have. Thank you.
That is the first presentation from Colombia. Again, as Daniela was saying, we're welcoming any questions you may have about this very interesting presentation regarding Roman concrete and its comparison and sustainability. So go ahead.
Hector, do you have a question?
Yes, I do. Your study concludes that the production method, particularly the fuel selection, had a greater impact than the Roman concrete years, maybe?
Yeah, thank you for that question. I would say a combination of both. When I mentioned that the mixture itself did not offer much less CO2 emissions than the modern counterparts is because modern concrete is already using supplementary cementitious materials in order to reduce that clinker to cement ratio that we typically see in our cement blends. So we already implemented that. I think that the study also was able to see that implementing alternative fuels and now with these new developments of how do we electrify the supply chain, then they can see even greater benefits from decarbonizing the entire value chain of the concrete production. So that's what I meant to say, not so much that now the formulations are not, we need to consider those because actually there's been a lot of studies recently that have demonstrated that Roman formulations also contain self-healing properties. So I would say, how can we harvest that historical wisdom with our modern technology to be able to further help decarbonizing the sector? That would be the main takeaway.
Okay, thank you. There is a question here in the chat. Is these Roman structures, are they the same materials that are we using today on construction?
Not necessarily the same recipe. So right now what we use is the majority of our concrete mixes are based on Portland cement. In Portland cement, the main ingredient is clinker. Clinker is something that we manufacture in a kiln, which is a big oven, and the temperatures are higher. But the main raw material the Romans used was limestone, and that's the main raw material that we continue to use. So the Romans used limestone. They obtained calcium oxide or calcium hydroxide, and then which we call typically lime or flat lime, and then they combine it with volcanic ash. So eventually that turned into binding phases that we see in our modern concrete and our modern cement blends, but that took a slower time to be produced because of the pozzolanic reaction that it involves. With clinker nowadays, when we see it in Portland cement, it starts acting quicker, it starts hydrating and immediately producing these binding phases. So that's why we see earlier strengths being developed faster, and that's how we are able to keep up with the demand and the construction as we see it nowadays. So that would be the main difference. So we have similar raw materials, but the recipes are different. The way they act right now and the way they hydrate and they combine into binding phases, that they take different paths there.
Okay. Last quick question. You discussed the importance of longer service life in reducing life cycle emissions. So is there a way, or how can we incorporate maintenance and repair strategies in future life cycle assessments to better compare those old Roman concrete inspired structures and new modern ones?
That's a great question. How can it be taken into account? Well, ideally, we should be looking into how to there's different applications, right? So not all concrete mixes go to the same sectors. So we have buildings, they last a specific amount of time, and then we have shorter lived applications, street, highways, etc. So we also have to look into the study. I didn't explain that in the video, but there's some aspects that we didn't include it because it was a preliminary assessment. So we didn't include the fact that modern concrete, mainly structural elements, are reinforced with steel. And then Roman concrete was not reinforced, so their structures were not reinforced. So we don't have that way of compare one by one. We see that their structures, some of them are still standing to this day, but they were not reinforced, so corrosion was not a problem for this type of structure. So that's something that we need to consider when we're time for maintenance and repair. And also beyond that, how do we do at the end of the life cycle is something that we should be thinking of. How do we design and build concrete elements, thinking about deconstruction of disassemblage somehow to be able to repurpose them somewhere. One thing that I mentioned briefly, but I didn't specify, was that in our models we were looking at in-use longevity, which is corresponds to how long a building or a street or highway can remain functionally in service. But we did not take into account, of course, that new demand for new materials for new construction, right? Because we're also expanding new construction. Also, building codes could change, so that could involve some retrofit of some structural elements in different parts of the world. So, incorporating those aspects, those elements could help enhance the modeling and then therefore the results.
Awesome. Thank you so much. Really, really interesting topic.
Hello, Gonzalo. I think it's time to move to the next presentation. It's a little bit longer than Daniela's. Thank you, Daniela. Very interesting.
Of course.
Go ahead, Gonzalo.
Thank you.
Thank you, of course. Well, I'm honored to present our next speaker, Carlos Ospina. Carlos is a fellow of ACI with 35 years of professional experience and 25 years of professional experience in marine infrastructure. He's the vice president of Moffett & Nichol in Houston. He's a member of ACI 318, former chair of 318F. And today he's a member of several committees, but today he'll be talking about a very related topic to the latest events in Venezuela, but it's basically practical considerations of seismic resistant design of marine infrastructure. So again, in honor of time, let's look at Carlos' presentation and then we'll look at questions.
My name is Carlos Ospina. I work for Moffett & Nichol in Houston, where I oversee the design and development of marine infrastructure projects in Latin America and the Gulf region. For the next 20 to 25 minutes, so we're going to be talking about seismic design of pile-supported piers and wharfs with precast concrete deck elements. This is slide that you see shows the typical structure that we're going to be talking about today. It is a pile-supported dock or wharf. The structure is located near shore. There are a few peculiarities about this structure. Notice the piles are very long, very slender. There's lots of them. And the structure also supports very heavy loading, in this case some ship-to-shore container cranes. So if you locate this facility of this kind in a region of high seismicity, now you understand the challenges associated with the design assignment. Traditional references that we use for the seismic design of this type of structures are the ASC COPRI 61 2014 standard, seismic design of piers and wharfs, and the PIANC Working Group 34 2001 guidelines, together with a book that was published by PIANC in 2001, where the content of the guidelines was substantially expanded. The good news is there are upcoming revisions to these two documents. Later this year, we're going to get to see the AC 6126 version. We're in the process of balloting that. I'm responsible, together with John Paul Smith, of Chapter 7, detailing and design of pile-to-deck connections. And PIANC Working Group 225, which is a new group that was created 5 years ago, will be publishing the updated guidelines with emphasis on port structures in general, their seismic design. So this document is coming up later this year. And for that document, I'm also in charge of the best design practices chapter, which is Chapter 7 as well, together with Dr. Smith from Seattle University. Basic concept behind the use of precast concrete elements in the deck is to accelerate construction. Imagine, you are in the middle of the sea, or you are working over water, and you can have an idea of how complicated it is to transport, produce the concrete, and create the mixes and construct everything with cast-in-place concrete. It is just difficult, and so this leads to the use of precast elements and just to accelerate this type of construction. The goal is to emulate the behavior of a cast-in-place concrete structure. And the challenges, as you can see, is how to ensure that continuity of all these elements. The design of connections is particularly relevant. We need to make sure that structural integrity is complied with. We need to preserve redundancy if it exists. This is work that cannot be done by just anybody. The contractor needs to have expertise on precasting, the handling of precast elements, their transportation, their erection and connectivity on site. And of course, for the designer viewpoint, the analysis and design of this is in stages is very important. A typical pier wharf construction sequence proceeds like this. After the pile is installed, and a subcap is provided, precast elements are positioned and then connected together. Then they provide support to precast deck elements, and followed by concrete topping that makes the whole thing a unit, work as a unit. The stage deck analysis is very important. There is a message that I would like to convey here, is that the precast beam is like an elephant. Doesn't forget. It never forgets. The deck constructed this way has to account for the fact that that construction doesn't take place just in one shot. It takes place in multiple steps, and so for every step, each member will be subject to specific boundary conditions, specific forces, reactions, applied moments, and whatnot. And all of these conditions need to be added up in a form of a bookkeeping form, just to make sure that we're not leaving anything out. So in this case, as everything starts with precast beam supported in simply supported condition, and after they get connected, and as you add concrete, fresh concrete on top, and as you place more stuff on them, the shears and moments associated with these beams will change, and also the cross-sectional properties, right? And so this makes stage construction a very important matter and a very important consideration when designing for this. Now, this is for gravity loads, and so how to handle seismic. Well, for that you need to keep track of all those forces as well, and when you have to combine those with the forces associated with seismic, then you have the good picture of what you're dealing with. The design of the joints is particularly key, because this is it very much ensures that the structure is going to behave according to plan. Seismic design philosophy just follows this very well-known analogy of the chain, where if you want some ductility out of it and you provide a link that is expected to be ductile, ductility is achieved only in the links adjacent near the ductile link are stronger, right? And this principle has been presented by many of our founding fathers of the structural engineering in the past, and I'm not going to elaborate on that, but just to say that this is the principle that we're going to be following here. For the specific case of this type of construction, wharfs and piers, the philosophy is similar to that of bridges, and which is opposite to that of buildings. So in wharfs and piers, we follow what is called the strong beam, weak column, or weak pile approach, which is similar to bridges. So in this case, the damage takes place in the piles, right? The piles have developed hinges, top and bottom, as a form to absorb, dissipate energy, and the deck stays almost elastic. And it's important that it stays elastic because of the heavy, expensive, fancy equipment that operates on top. Pile deck connections are either full or partial moment connections. And the good thing about this is the designer fully controls how much moment and forces get transferred from the piles up to the deck. Remember that as the ground moves or shakes, the inertial response of the structure, the piles communicate, transfer forces and moments to the deck. And so that connection is designed by the professional in charge of that design. And so it controls how much moment, how much forces get transferred to the deck. So it's critical to determine the right amount of bending that gets transferred, that the piles get to transfer to the deck. And as long as we comply with certain values, of limits of deformations for different components, we're fine. We're following what the standard asks us to do. Seismic resistant elements are typically the piles, and in the case of a margin that works like this, you have the piles. The more rigid piles are the ones near the shore, which have the shorter length, so hinges are expected to form there. And just as we are doing that, we're also trying to prevent the brittle shear failures in these piles. As an aside, we're going to look briefly at the response of batter piles in the past. I mean, for seismic, they are not recommended because they tend to attract quite a bit of lateral load. And therefore, unless you make adjustments to the connection with the deck, you're going to have shear failures at the top of those piles. And so there's evidence of this in Loma Prieta and Turkey and many other events. Batter piles are important. We're not saying that batter piles should be avoided in regions of high seismicity or moderate seismicity. We're saying that if you need them to provide lateral stiffness to the structure, you need to be careful when you connect them to the deck to try to avoid the damage that I just showed. Seismic capacity protection is a very important concept to follow. Essentially it says that it calls for the deck to stay elastic with a little bit of cracking, regardless of pile damage or deformation. And it is achieved by simply, because I know how much moment I'm transferring from the piles to the deck, I'm simply defining or designing the pile to deck connections on the deck for a moment that is slightly larger than that moment that the piles transferred. So in this case, it's 25% more. If a pile stays elastic, then the 1.25 is applied to the 25% increase is applied to the maximum elastic moment, not to the MP value. The MP is the probable maximum probable flexural strength of the pile. The shear, because of the brittle nature, shear in the piles is a capacity protected action. In a graph, this is shown in the form of seismic load applied in the longitudinal direction. Imagine all these moments transferred by the piles. So whatever the red lines, the red moments are applied on the structure, we have the resistance is offered by the deck. It's important is to make sure that we resist all what you see in at the top of the piles, properly factored by this 25% factor. And the slide where it says if you're transferring 25% more, then what this means is that a thin deck is going to crack a lot as these piles transfer this amount of moment, and so to be able to provide capacity protection, you need a thick enough deck so that you can resist the factor moment that is transferred from the piles to the deck. And so it is with time you develop a skill to understand if just by looking at the deck you get a good feeling if the deck is capacity protected or not. To design the connections of all these different deck precast elements, the mandatory source of information is research that the bridge folks have done. So Transportation Research Board or Federal Highway Administration have done a lot of work examining how to provide continuity in how to connect precast elements in this type of construction. So we're using that. And the pioneers in the seismic design of marine infrastructure got this information and adapted it. to our needs. So let's say 50 years ago, they were tested the PCA on beams, bridge girders with hooked ends, and so the provisions were developed to provide connectivity between them, and the tests were conducted on the connection to ensure that the whole connection would stay solid during cyclic loading. This is an example of something done by Washington Department of Transportation, which you can see the two girders in the end girders, the girder ends in yellow color with the extended bars and connected right on top of a subcap or a pile cap, and with all the shear reinforcement and joint reinforcement that goes in the joint, just to make sure that the two girders are continuous. So in this type of construction, it's nothing other than in this case, you have the pile, the subcap, and the precast elements landing on top. And you have a cast-in-place concrete, with precast panels, concrete topping, proper evaluation of where you calculate the negative moment demand of the precast elements. And then what we began discussing and introducing to the standard is just how to provide this, how to define the amount of reinforcement to provide continuity between the ends of the precast beams. And so as long as you provide sufficient reinforcement in the form of either contact or non-contact lap splices, you are good to go. So you provide enough bars at the bottom and hoops and whatnot, then you have a very solid joint that can provide good continuity between the girder ends. So all you need to do, just to understand what the joint reinforcement is doing, is to develop a series of strut and tie models, and because of equilibrium, and you can find that the forces on the horizontal ties and together with diagonal compressions are developed between the hooked end portions of the bottom reinforcement and the joint reinforcement provide the proper path for force transfer between one girder to the other. In plan, that strut and tie model looks like this. And just to calculate the amount of reinforcement, this is how we're recommending this expression that was originally developed by Washington Department of Transportation. Simply defines the amount of joint reinforcement necessary just to connect or develop tension from one side to the other. When you have more complex conditions, introducing, let's say, lateral loads, and then you can also use the strut and tie model to monitor or to get a feeling of forces and flow of forces and amount of tension and compression in the joint. So this leads to adjustments in the amount of joint reinforcement depending on the conditions and that the joint is going to be subjected to. Samples of things that you could do to provide continuity, and that's through the headed reinforcement shown on the left, or double hooked bars, and just simply drop them. There's no guidance, unfortunately, from 318 on how to do this and how to define the LST, the development length, or the splice length between the two. But if you assume that this LST is greater than the development length of a hook bar, and that 1.3 factor comes to play. It could be reduced if you assume that you provide sufficient joint reinforcement using the provision that we saw earlier to try to minimize the size of that subcap that supports the precast beams. Let's look at different type of connections. So these are connections that involve steel pipe piles, and as presented in the upcoming version of the AC 61 standard. The most popular ones are from left to right, the second and the third, which make use of a reinforced concrete plug and the use of dowels. And the dowel, in essence, what it does is just it transforms the steel pipe pile into a reinforced concrete member to transfer the forces and moments from the pile up to the deck. And these are the connections involving precast concrete piles or cast-in-place concrete piles. The same concept, except that now you have a concrete pile with dowels installed at the top, and that enable the transfer of moments and forces from the pile to the deck. The concrete pile plug is very, very common when you see connections involving steel pipe piles, and that plug is cast in place. When you That's the most common form, and the plug is nothing other than a subterfuge to develop the couple, the moment, at the top of the pile. And so there have been recent efforts to replace the cast-in-place concrete plug with precast plug units to accelerate construction. And as long as you can try to mimic that, right? You can mimic that with a plug that resembles the cast-in-place plug, and you fill out the annulus between the precast plug and the surrounding casing of the pile. Then you're good to go. These plugs support the precast elements on top. And the references that you see on the screen show the rationale behind the development of the plug. In an ordinary plug connection, we assume that connection at the top takes between 30 to 50% the MPE at the bottom of the pile, or at the steel portion of the pile. If a reinforced concrete plug is too strong, the moment is much greater than it could be, much greater than MPE, and that could lead to problems in the in-ground region of the pile. It could even increase rotations, and it could generate local buckling problems. How to predict that MPE? So MPE is, you have to understand that you need to properly account for the presence of concrete. You just cannot disregard that there is concrete there, right? And how composite the section adds depends on that, on how the steel casing and the infill, the concrete, behave, right? And how thick or thin that steel casing is, right? And so MPE, the evaluation of MPE is very important. Remember, you're controlling the capacity protection of the deck based on that MPE assumption. Flexural capacity of a plug is affected by axial load level, and we know that because you're familiar with reinforced concrete column design. Now, not all the precast pile plugs are supported the same way, so you need to be careful when evaluating the effect of axial load on bending. When I mentioned local buckling, so for local buckling, you need to be careful with the size of the steel pipe pile relative to the thickness of it. And so as the D/T ratio increases, the chances of local buckling increase. So you need to be very careful with defining the so-called critical strain. You need to be aware that the provisions in AC 61 are not always conservative, and there may be actually circumstances where you just can't achieve the target strains that the standard expects you to follow, especially for the life safety condition. You need to have a pile that is super compact to achieve those limiting strains. So you need to be careful when local buckling is a possibility. This shows the effect of local buckling on the response of a pile. So if you want to do a pushover and expect full development of hinges and without losing capacity or generating instabilities, you need to make sure you prevent the local buckling. Otherwise, your response could be shortened substantially. We're going to quickly talk about, we have 5 minutes to talk about a representative project where you're going to see the use of precast deck elements and how we accounted for that in design and also in construction. The project is located in Veracruz, Mexico, in the area shown the red oval. The marginal wharf, nearly 1,800 feet long and 114 feet wide. It's a marginal wharf, completely encased by existing structures. The soil stratigraphy shows a combination of, multiple strata of clay sands, and the soils display setup. That means that the piles that get driven into it gain capacity with time. This is a cross-section of the wharf. It's not quite the typical marginal wharf where you have a very steep slope, but this is because there is a structure behind, there was a need to have a steep slope behind, but it is marginal because it's against the shoreline. So every bent has 6 piles, and the ones on grids A and F support heavy cranes. This plan shows a pile plan. You have bends every 7.5 meters. This plan shows precast subcaps and precast beams. Notice the beams in the longitudinal direction providing support to the crane beams. And we also have intermediate piles in between vents because of the high loads that you have over those beams. The slide shows the way we monitor the geotechnical capacity of the piles and the status of the piles. There are piles that were installed, piles that haven't been cut off yet, and piles that have been. These piles were subject to a very thorough pile testing program because of the challenges introduced by the soil. In some cases, the piles double capacity with time. This picture shows the steel pipe piles. And you can see the coated end on the left, all piles installed, very well positioned because of the nature of construction. So you have two top-down systems. The one on the right is responsible for installing the piles. The machine, the crane installs piles and then crawls over them and goes in a linear way and moves in linear fashion, whereas the second front installs the precast elements that make up for the deck. This is the precast pile plug. So it gets inserted in the existing previously driven and cut off steel pipe piles. You can see the crane, the piling rig on the right, and the precast deck element installer on the left. You can see a close-up showing the installation of subcaps, beams, transverse beams, deck panels, added topping, and for the space between deck panels as well. It shows the entire construction in one shot, showing the piles at the front and the decking proceeding behind. It's a very, very fast procedure. This particular project, nearly 540 piles were installed in 6 months. Very, very, very capable contractor, Simesa Solitanchpachi, and the entire work, 1,800 feet, built in 12 months. This is because of this technique. Just to conclude, seismic design of piers and wharfs with precast deck elements has reached adulthood, in the sense that the standards are right now more provide very specific recommendations on how to deal with that, with the precasting and nature and the stage construction nature of these structures. The most appealing application by far is the accelerated construction of piers and wharfs, so it's supported on piles and where massive use of precast elements is adopted for lots of reasons, because you want to finish earlier, because you want to get ready for the bringing new equipment and whatnot, and because you want to build things fast. The design and detailing of these elements is very important, and the way they are connected is critical just for an adequate seismic response of the pier and wharf structure. I want to conclude by acknowledging first of all, thanking the invitation from ACI Colombia to present, and express my thanks to ASC 61 Committee and the PIANC, the International Association of Navigation Working Group 225, is responsible also for this other document that we spoke about. These committees have been very actively working on the development of these new provisions and updating the existing provisions, and so thanks are extended to all these members, and particularly my colleague Professor John Paul Smith from Seattle University, who's co-lead of these chapters that I spoke to you about in these two standards, and Moffat Nickel Columbia, which is actually one of the groups within Moffat Nickel that gets to get involved in this type of designs, and so we implement many of what you see, plenty of what you see in these slides in practice. So thank you so much. In case of questions, I'd be more than happy to answer them, and I assume that ACI is going to provide the proper mechanism for communicating these questions. And so thank you so much. That's my email address on the screen, and thanks a lot.
Thanks, Carlos. I think we have maybe one question, and then we have to give it up to Ibracom. So I don't know if there's one particular question we can answer.
Yes, I do have one. Thank you for your presentation. Seismic design is always a great topic. For precast deck systems in high seismic regions, what would be the most common mistakes that you see on pile to deck or precast to precast connections?
I would say, well, first of all, good afternoon. Hello, everybody. I would say the absence of proper projecting bars in the precast elements that provide continuity. We witnessed so many failures and so many problems, not only in areas of high seismicity, but also in areas where you have hurricane activity. We've seen precast deck elements literally flying up and away from support because of that lack of connections. Biggest challenge that we face is we are, I would say, fortunate enough that in 2014 we developed a standard finally for seismic design of this type of structures. But there is room for more. There are initiatives by PCI to work on a design of port structures. I'm planting a seed to HCI. I think it would be nice to either collaborate to PCI with PCI or have our own committee that looks at these things in the environment where we're talking about, which is marine infrastructure. Lots of stuff is said about buildings and bridges, and you have the entire world trading and doing whatnot in marine terminals, and there is little I would say information available just for the design of these facilities. So yeah, I just take this as an opportunity to spread the voice a little bit about this need.
Thank you very much. Thank you, Carlos. Thank you, Daniela. Gonzalo, thank you so much. I think we will be traveling now to Brazil. Rafael, I don't know if you are already there. So if you could start.
I'm here.